So problem number 7 in the Advanced Classical Mechanics Practice Final Exam. So consider the transformation Q equals ln P equals QP with Q is greater than 0. Part A, determine whether this transformation is canonical using Poisson brackets. Part B, find a generating function for the transformation. Part C, transform the Hamiltonian HQ, P equals P squared over 2m plus AQ squared into the new variables. Part D, derive the new Hamiltonian equations. And Part E, verify consistency with the original equations of motion. And for brevity, if you see a lowercase p, I'm going to call it p. Uppercase p, I'm going to call it p. The lowercase p is for the original, and then uppercase p is for the transformed respective momenta. So let's begin the canonical transformations in Poisson brackets. Given q equals ln q, p equals qp, where q is greater than 0. Invert the transformation. Q equals e to the q, and p equals p to the e to the negative q. So the Poisson bracket is here. This qp is partial derivative of q with respect to lowercase q, partial derivative of p with respect to lowercase p, minus partial derivative of q with respect to lowercase p, times partial derivative of p over partial derivative of p with respect to lowercase q. So this dq, partial dq with respect to lowercase q equals 1 over q. Partial derivative here of p with respect to lowercase p is q. And partial derivative of capital Q with respect to lowercase p equals 0. So therefore this Poisson bracket equals 1 over q times q minus 0, which is 1. So the Poisson bracket here equals 1, and therefore the transformation is canonical. Okay, moving along here into part B, find the generating function for the transformation. So to find a generating function, we're going to use a type 2 generating function, f sub 2 q comma p, satisfying this p equals partial derivative f sub 2 with respect to lowercase q, and capital Q equals partial derivative f sub 2 with respect to capital P. So since Q equals ln lowercase q, that we want to lead to partial derivative of f sub 2 with respect to capital P equals ln lowercase q. So we choose f sub 2 q comma capital P equals capital P ln lowercase q. And then from there what we get is P lowercase p equals partial derivative of f sub 2 with respect to lowercase q, which is that p over q. So capital P equals lowercase q, lowercase p, which matches the given transformation. Okay, so leading into the Hamiltonian portion here, so we're going to transform the Hamiltonian and then derive the new Hamiltonian equations and verify for the last page here. So I'm going to go through this quickly. I'm just going to say P and Q for these for sake of brevity, and on the page or the capitals and the lower cases are distinguished from each other. So let's just focus this. Sorry about that. Oops. So let's see if this comes in focus. Okay, so we transform the Hamiltonian now. So up here in the first line, transform the Hamiltonian HQP equals P squared over 2m plus AQ squared. So using this Q equals e to the Q, P to the equals P equals P e to the negative Q. We're going to get the following: KQ comma P equals P squared e to the negative 2Q over 2m plus A e to the 2Q. So the transformed Hamiltonian is K Q comma P equals P squared over 2m e to the negative 2Q plus A e to the 2Q. So Hamilton's equations in the new variables are Q dot equals partial derivative of K with respect to P, and that equals P over m e to the negative 2Q. So q dot equals p over m e to the negative 2q, and also p dot equals negative partial k with respect to capital Q, and here partial k derivative with respect to q equals negative p squared over m e to the negative 2q plus 2a e to the 2q. So this capital P dot equals this p squared over m e to the negative 2q minus 2a e to the 2q. And we're going to now what we're going to do is we're going to check for the consistency with the original equation. So the original Hamiltonian gives q dot equals partial of h with respect to p equals p over m, and this p dot equals negative partial derivative of h with respect to q equals negative 2aq. And since capital Q is ln of lowercase q, q dot equals lowercase q dot over lowercase q. And using this lowercase q dot, that equals p over m. And capital Q dot equals p over mq. However, p equals qp, so this p, lowercase p, equals capital P over lowercase q. Going back to this side, so q dot equals capital P over mq squared. And since q equals e to the capital Q, then lowercase q squared equals e to the 2 capital Q, and q dot equals p over m e to the negative 2q. And this agrees with the transformed Hamilton equation. Now from there, next what we could do, starting here, so next p equals qp, so p dot equals q dot p plus qp dot. And using here q dot equals p over m, p dot equals negative 2aq, and that capital P dot equals p squared over m minus 2aq squared. So lowercase p equals capital P e to the negative q, and lowercase q equals e to the capital Q. So then p dot equals p squared e to the negative 2q over m minus 2ae to the 2q. And so p dot equals p squared over m e to the negative 2q minus 2ae to the 2q, which agrees with the transformed Hamilton equation. So we could conclude here, capital Q equals ln lowercase q, capital P equals lowercase qp, and there's a canonical transformation generated by f sub 2 q comma p equals p ln q. And the transformed Hamiltonian is k q comma p equals p squared over 2m e to the negative 2q plus a e to the 2q. Okay, so that's all for this problem. Thank you very much and have a great day.